Good morning. So I promised to try to help explain equilibrium a little better after that discussion we had last week. So I'm going to start by saying a definition is good, and if I've got a definition here on my computer, number one, it says a state in which opposing forces or influences are balanced. And the second definition, and this is coming out of Google, a state of physical balance. So when I was a kid, that was explained in two ways. We had a stable equilibrium, and if I hold up this bolt, and if it goes one way or the other, it hangs straight, and that reaches its stable equilibrium where forces are in balance to keep the bolt from moving. On the other hand, if I put it down, let me move the screen here and show you the bolt. Now that bolt is in an unstable equilibrium. This is an example that I got when I was a student, in which case everything is in balance, but if there's a slight movement, it goes out of balance, and that's an unstable equilibrium. So definitions are great and examples are good, but the dynamics of equilibrium are what I wanted you folks to understand better, and I have another demonstration which hopefully will give you some insight into some of the more complex aspects of thinking about equilibrium, not just the simple definition or that simple example that I showed you with the bolt. Okay, what I have here is I have a faucet dripping into a plastic bottle with its head cut off, and on the side over here you can see the water's running out. So this has established a balance. It hasn't overflowed because the amount of water flowing in is equal to the amount of water flowing out. And if I measure the equilibrium level with my little ruler, the level is right at 1.5 inches. So 1.5 inches down is the water level, and the input is equal to the output. So the equilibrium dynamics question is, what happens if I lower the rate of water? So you can think about it, and I'm going to do that in a second. Let me hold here a second. Okay, so the water is now dripping more slowly. You'll notice down here the water used to be shooting out more straight. Now it's kind of dribbling off the end. Here's the water. You can see it right here. It's going down, and it's not. It used to be shooting straight out much farther. So if I go down here, and I've been letting it run for a while, and if I go down here and I measure the level down to the water, it's at 5.5 inches. Okay, so that's a new equilibrium level. Less water coming out, new equilibrium level. So that's an equilibrium dynamic. So I'm going to turn the water back up to what it was before, a little stronger, and I'll let it equilibrate and come back. Okay, so I've increased the volume of the water again back to what it's almost what it was before. You can see the water down here is shooting out under higher pressure, and I couldn't get it exactly to 1.5 inches, but it's about an equilibrium level of the water is about 1 inch down. So now the question is, what happens if I take my drill and I drill a bigger hole in the side? All right, I'm going to have to somehow turn the water off here. I'm going to leave the water amount the same, but turn. Okay, so now I'm just going to make the hole in the side of this thing larger by drilling a bigger hole. Whoa. Alright. And what do you think is going to happen? So I'll let it equilibrate and come back in a few minutes. Okay, so I've drilled the hole, filled it back up with water. I let the water drip in there, and now I'm going to tell you where the equilibrium level of the water is. And it's about 5.5 inches down in there. Alright, so the question for you is, you can see that the water is streaming out. It's not streaming out as hard. It's a larger hole. this volume is the same as it was before. So the water level has reached a new equilibrium. And it's this equilibrium dynamics and the feedbacks between it that I'd like to talk about using this as an example. So the equilibrium dynamics that I just gave you an example of, I'm going to suggest are pretty much the same as the one that I was talking about in class relative to the forest floor, and why when you walk in the forest floor do you walk on a certain level of material. And so the analogy here is that there is a negative feedback involved in this particular equilibrium dynamics. The more water you have, the higher the pressure that is generated at the hole, which means the more water that feeds back. So that's a negative feedback. The more water you have, the higher the flow, which is going to be counter to this thing filling up and overflowing. And the equilibrium level that is found just matches the input rate to the pressure that generates the increased output rate to equilibrate the two things and put them in balance. So the definition of balance holds when it reaches equilibrium, but I would argue that the definition doesn't really tell you the whole story. The whole story is about understanding how these dynamics change as a result of the negative feedback. And the negative feedback that I explained relative to the forest floor is the more forest floor you have, the thicker it is, the more substrate, the more surface area there is for bacteria and fungi to operate on, and therefore the decomposition rate increases. So the decomposition rate will increase with the volume until it just matches the rate that the litter falls on the forest floor.